So now I think we'll slowly get started. So welcome everybody to this webinar about modular Power-to-X systems with 25 years lifetime in harsh environments. This webinar is a result of a project funded by Energy Cluster Denmark in combination with some of the other work we do here at Force Technology. Because we are quite many here, your microphones have been muted and your videos turned off. If you have any questions during the presentations, please write them in the chat, and then hopefully we'll have time to answer some of them towards the end of the webinar. The slides will also be distributed after the event, and the webinar is also recorded. So this is just the agenda for what we'll cover today. We'll start with a few introductory words from me. My name is Erik Brock, and I'm an analysis specialist at Force Technology. And then after that, my expert colleagues, Nana, Troels, and Kim, will talk about some of the results of their work on modular Power-to-X systems, focusing on the shell around the module, the seawater cooling systems, and electronics and climate controls, respectively. And then we'll have a few words from some of our project partners before we end with some closing remarks and hopefully some questions and time to answer them from all of you. So that's what we'll cover today. First, just the background here is, of course, as you all know, Power-to-X is a topic that is getting a lot of attention because we need to store energy from intermittent sources like wind or solar. And there has been a particular interest in modular solutions. And these modules can be either by the individual wind turbines, as you can see in the picture here from Aquaventus, or it could be on energy islands or platforms or on the coast. We have a feeling that from our conversations with the companies in the sector that there's an expectation for 25 or even 30 years lifetime of these modules. And this is going to be challenging because the environment, especially offshore, is very harsh with high humidity and salt concentration. So that means that it's going to be very important to choose the right designs and the right materials to achieve a lifetime that approaches this 25 years or even more. Finally, of course, maintenance is expensive and difficult on an offshore installation. So that is something that needs to be limited in order to keep the price down at a reasonable level. And then you can say there's also further complications with the hydrogen production because of the safety issues around hydrogen. So if we're going to roll out Power-to-X on a large scale, this of course means that there's a large business potential. But it also means that there are a need for new innovation and solutions to new problems. And some of this is related to the design and materials choice. And this is what we'll talk about today. So Force Technology has a lot of experience with corrosion protection, and often we inspect some of the results of what happens when something has not been properly corrosion protected for the intended use environment. And with this background and experience, we have had some talks or interviews with a lot of companies that are interested in Power-to-X and the Power-to-X market, and found that most often the company doesn't have the full picture. One company typically produce the electrolyzer, another company produce a container, another one builds wind farms, another one is in charge of the maintenance, and so on. So sometimes we have the feeling that some of the difficult problems are not really handled by anyone. It's maybe not always the case, but at least often the case is our experience that this is something that is kind of something that you think maybe lies with someone else in the value chain. I don't know if it's because it's difficult or because you just haven't really the complete overview of what happens in the value chain. So a Power-to-X module is a complicated system, contains many parts, and you need to take it all into account. It needs to be produced, transported, installed, integrated into some system, and it needs to be serviced while it's in service. And all of this is something you have to think about. If you have a shell that is container, a modified container, can that last for 25 years? What about cooling water intake? What about sensitive electronics inside? And what environment do you need to keep inside the module? That is something that we identified some of the problems that were mostly expressed as interesting by companies in the Power-to-X value chain. And this is then something we have been investigating in this Energy Cluster Denmark project with almost the same name as this webinar. And you can see the name of the companies and their logos at the bottom. Those are the partners in the project. And the main thing we did in the project was deliver some initial input to design specifications. So nothing like a final design, but more lists of do's and don'ts and what do you need to consider in these 4 sub work packages or work groups. And one is about the shell, one is about integrations and submerged parts. And here integrations means basically anything that comes in or out of the container or the shell, and electronics and climate control system. And this is then will be the basis of what you'll hear today. And by the way, I should say just quickly that I've been talking about hydrogen production, but of course some of these problems we are addressing are more general, and it could be other modular units. For example, instead of a fuel cell, it could instead of the hydrogen production, it could be a fuel cell. So you could have a power unit instead of a hydrogen production unit, and then it wouldn't maybe be Power-to-X, but X to power instead. But you would face many of the same issues. So I think with that, I'll give the word to Nana to talk about the shell. I hope you're there, Nana.
I'm here. Thank you, Eric.
That's good.
I'll see if I can take control over this. Let's see if it works. Okay. Yes, so in my group in activity 2, we've been working with the shell, the modular solution, the typically container, a modified container, and the basis that we have experienced that depending on who people are choosing a supplier for their container and how it's modified, it's modified more or less, and sometimes it's not really fit for offshore solutions, or in fact not fit for purposes where it's not maintained all the time. So this is the basis for this discussions. Let's see. Okay, Eric, it doesn't want to let me control it. It seems. Can I go?
I see you're trying it.
Well, use the arrows.
Yeah, I am, but it doesn't work. And in a few seconds, I've been in the end of the. Okay, Eric, will you take over, please?
Yeah, okay. I'll just let me know when to.
Okay, you can change slide now.
Yes, now I'm not allowed to. Hang
I'm
on.
stopping control. So.
Yes. Let's see.
Now you could.
There you go.
Be allowed. There you go. Okay. So I'm going to start presenting the activity group and the original purpose and how the result we ended up with, what we learned through the project, and a bit of a future demo idea. Next slide, please. Okay. The participants in this group was DC Supply, that is actually modifying containers, building them for special purposes. And Morrison and CS Electric, who are using these shells, these modules also for different purposes. Not all necessarily for Power-to-X, but for other purposes where modules are necessary or actually give a lot of flexibility, and where they are also in the same harsh environment. Okay, next one. I'd say the original purpose was to find the perfect design for a module, and to a unit that would attain long durability in harsh environment, and that was how we started out. We sat down we had 3 workshops actually, where we were visiting each other. So we have been visiting all the different participants, and we were discussing all the experiences we've had with modules that we had met through our professional experience, and what pros and cons there were of all the different solutions, because we meet a lot of different solutions during our time. Next one, please. And all those discussions we ended up listing in a do and don't list, where we were discussing all the pros and cons of all the different solutions. Here I've just shown a very small piece of it, considering paint specification and choice of paint system and steel preparation, and also design. And when we're talking design here, we are basically talking about design for painting, because not all designs are very easy to paint or to do any repairing or maintenance on. So that's been it. Next slide, please. Okay. And the headlines in our do's and don't list was paint as corrosion protection. That's what you've seen a part of. And that was especially about the design and the corrosion protection specification, because we often meet problems where we have a paint system has been specified, but maybe not as detailed as you could, and then you're not receiving what you actually thought you would receive. So that's been a part of the discussion too. We've been discussing different assembly methods. That's like welds, rivets, bolts, hinges, different material combinations, and how to avoid some of the built-in risks in that. So we've listed a lot there too. Then it was also been discussed how to lead in pipes and cables in a good way through originally just a basic container side. It needs some more stability, and you need these leads in to be tight, to protect the environment inside. And then we've also been discussing transport damages, because some of the special things about the modules is that you build them, you install them, and then you start transporting them, and they're really not treated very nice during transport. A lot of things on the outer surface are damaged during transport. So that has also been a discussion, how to avoid this and how to do on-site repairs and inspection, and what's the need for inspections and maintenance. So that's also been one of the headlines. Next slide, please. And I can say that what we learned during this workshop is that if we're going to do the ultimately perfect shell, it will be a lot more expensive than the modules we are building today. But we also found out that one design will not fit all purposes, or are not necessary for all purposes. So what this list is really useful for is to have the discussions about what do we need here, what will be the service life of this particular module, and where do we need to where do we need the perfect solution? Where is the next to perfect solutions just as good? Where do we have possibilities for maintenance and where don't we? So that is some of the learnings, and also, as I spoke of just before, the transport and maintenance options is just as important. Yes, next one, please. Yeah, and then we are at the moment working on the possibility of starting a demo project where we are trying to compare some of the do some tests on different different assembly solutions to see how they work out compared to one another. But that's still in project start. Okay, thank you.
Thank you, Nana. And I think then it's Troels next.
Yes.
Do you want me to carry on?
No, please give me the control. Yeah. Yeah, I'll give a short summary of our activity 5 or activity 4, this group. We looked at cooling water systems. No, it's not working. You take the control.
Okay.
Even though it worked in our.
It worked when we tested it before. Okay.
When we tried it.
Yeah.
Okay, so far. Activity 4, we looked at seawater cooling systems for PtX module. We were 5 participants in the group, and our general scope was to define and discuss and tackle the challenges we meet for a seawater cooling system. For a PtX module or electrolyzer, as shown at the right, we would need quite a big cooling system for a system like this. But we also discussed how if we should make a new project. I will come back to that. Please move on. So one of the challenges for a cooling water system operating in seawater is marine organisms. They tend to settle on the internal surfaces, as you see here. We have barnacles covering almost the entire surface, and this will disturb our operation of the cooling water system. We have lower flow, lower cool heat transfer, perhaps plugging of filters, and so on. Next one. And another issue is corrosion, of course. Seawater is extremely corrosive to most metals. If we take low alloy stainless steel or the common grades of stainless steel like IC316, it has limited corrosion resistance in seawater. These are 2 examples of severe corrosion. One at the left is a basket that has been in seawater for 4 years. It's almost gone. And the example at the right are some instrument tubings on a platform where we actually have corrosion from the outside, as shown by the cross section, almost penetrating the tubes. Next one. So for the discussion in our group, we use this work model. It's a schematic from the company Bolfilter, and it shows the basic components in the seawater cooling system. So we have a submerged pump, and we have filters, and we have a heat exchanger where we exchange heat from the electrolyzer. In this case, it's a transformer station shown, but it could have been an electrolyzer. So we exchange the heat there in a heat exchanger and then discharge the water to the sea again. And this is known as open loop cooling systems. The systems we were discussing was a centralized system where we have the electrolyzer on a platform, and we would actually need, for a 500 megawatt system, we would need about 1/3 of the power for cooling. So it's a quite big system. If we move the electrolyzer to the wind turbine foundation, it will perhaps have a power of 15 megawatt, and we will need 4 to 5 megawatt cooling. So these are some basic facts on the cooling systems we are talking about. Of course, materials is a big issue to avoid corrosion, but there is already a lot of knowledge about what materials to use. The special thing about the Power-to-X module is that it will operate almost constantly. So we will only have 2 or 3 days yearly to do maintenance on the cooling water system. And if you move on to the next one, please. Yeah, so there are some challenges. I will come back to that. But the most used concept of cooling water systems is one through, or the open loop system, that consists of the lift pump, some kind of anti-fouling chemical dosage, a filter, and a heat exchanger. For our project, we have been inspired by other projects, and the transformer stations for the existing wind farms, offshore wind farm, is I think what we can learn from when we are going to design new cooling systems. That we also know about at least 2 projects where they intend to move electrolyzers offshore, one in Holland and one in Germany. And in addition to this, we came over a new concept. It's called CoolWind. It's a Norwegian company where they actually intend to move the heat exchanger, place it on the seabed instead of having it on the platform. And by this, they can reduce chemical treatment and in the system, because they don't have actually circulation of seawater. So the next one, please, Egg. So in the group, we try to list all the challenges we will meet for a cooling water system. In the first case, the open loop system. And one forward, please. Yeah. And there's a lot of challenges, and we already know all these challenges from existing cooling water systems like ships or offshore platforms for oil and gas. But what's special for the Power-to-X systems I have encircled here, it's that we have an unmanned structure. So we don't have a 24-hour service on the system. It's perhaps one every year. It has to be very reliable, and it has to operate for 25 years, ideally. But these are some of the challenges we have to overcome. And the second one is the environmental concerns. There's an increasing focus on this. An open loop cooling water system will release some chemicals, chlorine or whatever you use to combat the fouling inside the system. And there are some rumors that the German authorities say they will ban the open loop system soon. So there's an motive to move away from the open loop to the closed loop. And we looked a little bit into this, if you move on. Torbjørn Schrøder from Copenhagen Pump, who will get the word later. He did some guiding calculations of for different pump heat exchanger configurations for either open loop or closed loop. And I'm not going into all the details, but what we see is that the closed loop heat exchanger is very expensive, at least for the moment, compared to an open loop system. So we need to find cheaper materials or smarter solutions in order to make this cooling system available and feasible. Okay, so let's go to the final one. So we had some quite interesting discussions and ideas, but we are not, you could say we are not finished yet. We didn't complete the work. We didn't expect to either. It's a quite small project, but from our discussions, we see at least 2 interesting projects that we could continue and apply for. One, making the closed loop system more cost optimal. As you saw before, the heat exchanger is extremely expensive. And the other one, if we want to go on with the open loop system, we should consider, can we make these more environmental friendly and use less chemicals? The authorities would like that, I'm sure. We haven't formed any project groups yet. Everything is open, so if you are interested, please contact us and perhaps we can set up a project. Okay, thank you for your attention.
Thank you, Troels. And the next up is Kim. And I guess I'll just keep the control of the slides.
You are doing so good, so we will keep it there.
Thank you.
So also, I would like to thank the project partners for their participants in we had 2 workshops, online workshops, where we had discussed and had good inputs from our partners with questions, comments, and good advice, and what is the hard thing to do. So I will look into the 2 work package now with the electronics and then the climatic cool system for the electronics. And it's well known, if we want to have long lifetime for electronics, we have to keep it temperature down. We have to keep the electronics away from polluted atmosphere, and we have to keep the relative humidity low. We have to avoid condensation. That is well known, but that is actually the challenge when we put electronics to offshore. Next one. So what we advise to do is to make what we call a thorough mission profile analysis. That means basically, and also my colleagues Troels and Nana mentioned it, that we have to know what is happening from production all on the way for shipment, loading, storage, and then into useful lives. And when we are in useful life, the 25 years, we also have to consider what will happen during the necessary maintenance task, because we might have made a very tight container, but from time to time we have to open it to do maintenance and service. We have to consider that as well. Next one, please. Another thing that is important for the electronics is the operating condition. How do we use the electronics? And for a modular Power-to-X system, this could be like 24/7 for a system that would be producing hydrogen. It might be a couple of hours per day for a system for a part-time energy generation. As you said, Erik, we can also produce electric power from hydrogen. And it could also be a backup system where we only use the hydrogen to power when the net is down or something like that. And of course, the operating conditions are very different for the electronics, and the challenges are also different. If we run for 24/7, then probably the greatest challenge is the high temperature. We need cooling, as you said, also for electronics. For condition 3, the greatest challenge could probably be humidity, because we don't have heat to get the relative humidity down. And then the condition 2 is a mix between those. I have added a reference here, a report where you can get inspiration to make mission profile analysis. Next one, please. If we take electronics and put it in these kind of missions that we have talked about here, it cannot withstand 25 years without some kind of protection. So we need that protection, and that's what we call climate control here in this project. Next one, please. So the purpose of the climate control is to ensure cool and dry conditions for the electronics. And this includes, it's not a complete list, but we have to have protection from the harsh outer environments. That is something with tightness. We have to remove excessive heat, the cooling, and we have to keep the relative humidity down. It can be done actively by dehumidification or desiccants or something like that, or it can be done passive if you can heat up stuff. Next one, please. It's when we talk about tightness, it's an electronics. It's a good idea to look into well-known standards, and one standard is IEC 6529. It gives some classification system for tightness from solid parts, from hands to finger to dust, and water from light rain, splashing, immersion, and high pressure cleaning. The system is very simple and very well known, and it's a part of a lot of requirements. But you should remember that it's only short testing time. It's not related to long lifetime, and it does not give any information of humidity ingress over time. So it's not a sufficient requirement for many years of trouble-free operation. Next one. And one discussion is when you have a system like that, we can start on system level where we have the entire container, or the subsystem, that's the cabinets with the electronic module inside, the module itself, or the printed circuit board, the green boards with the components on inside. And where to make this tightness where we protect it for humidity, that's not a trivial task. And you have to make some decision on system level in order to design this. Next one, please. And when we look in climatic control means of getting rid of heat, we have three fundamental ways to remove heat when we talk about electronics. We can have natural convection, we can have forced convection where we're using fans, and we can have liquid cooling. And we can be inspired by this example from an electric car, where you can see some of the power systems, they are cooled by liquid. Some of the processing units, medium power, they are fan cooled, and some of this not so much heat dissipating stuff like the lamps and things like that, they can be cooled by natural convection. So it's not that you have one solution that can fit all. Same thing is for the Power-to-X. Let's take the next one, Erik. Here's one example of how such a system could be. And we can see in the big compartment where we have all the tubing and the cylinders and stuff like that, we will have three small devices near the blue one. That is probably the electrolyzers or the stack, and they generate a lot of heat that is probably liquid cool, and the liquid cool will go up to the air coolers on the top, the big flat box with the three big fans on the top. But we can also see behind the yellow fence, we can see like two normal looking outdoor condition amplifiers that might cool the high voltage room where you can see the orange transformer, or the compartment to the right, most right, where you have the electronics one. They can be perhaps cooling that by air cooling. And you can also see in the left end of this one here, you can see that it seems to be an air intake into the big chemical room, and then there's also an air outlet where you have to control and filter so you don't get too much salt inside. So it's not the one means that fit all. You have to have a clear design specification. Next one. So when we come to this, to design this climate control system, as in any other systems, we need a detailed system requirement specification. Some of you called it the design specification. And when we have the specification, we need to make decision on strategy to obtain the proper design. And on the climate control system for a PtX system, we have to know something about the heat dissipation, the total, and for the subsystems, we have to know something about desired operating temperature for the electronics, desired humidity condition, and relevant pollutants. They can be internally from the chemicals inside the container, or they can be external like salt mist. And then we also have to need here, because 25 years is a long time and we need maintenance. So we need to include already here, what is the plan for the scheduled or needed maintenance. Of course, we also have considered the external requirements that is from authorities and stuff like that. And there are many more. And I have included here a reference to SPM report 81, that is giving examples of how you can specify it for electronics to have long lifetime. Next one, please. And then when you have a system in operation, even you have tried to make it tight and you have climate control, there is risk of humidity ingress for outdoor electronics. And we have to especially consider when we have service or maintenance operations where we open hatches or doors and let in stuff like salt mist and things like that. And continuous condition monitoring with focus on humidity and corrosion is useful to have assess the running risk of problems with the equipment. And here I've included 2 examples of some fairly novel sensors for that purpose. In a project called ELMAC, where we led by DTU, ELMAC is electronics manufactured for corrosions. We are working on developing a emission profiling sensor. It's on the 2 most left pictures. It's about the size of a small children's hand. In the red area, we have a humidity and temperature sensors. And beside the red circles, we have some grid patterns where one is protected and one is open. And when we measure the changes in behavior of these 2 patterns, we can measure corrosivity. Another thing we are working with is in a FORCE project, we call a performance contract, long-lived products, is what we call a moisture level indicator. That's basically a piece of the printed circuit board, a couple of square centimeters, where we make a special pattern, and then we can measure capacity change, because capacity change will change when we have humidity absorbed inside the printed circuit boards. We have made proof of concept for that, and we are now working with customers to get it out to check it in the real world. Next one. Just to show some other thing we're working with in the ELMAC project is classification of the external environment. And here are some example masks. There will be an app from this one where everyone can use, and then you can make classification, the good old Köppen zones as known from some IEC standards, but also some fairly new methods like dew point depression, where we have special focus on dew point, because dew point is relevant for risk of condensation. Next one. So come to conclusions. You cannot give in a 1-hour webinar all the do's and don'ts for electronics, because it's not a trivial task to obtain 25 years of lifetime. And actually, when you are in harsh environments like offshore, it cannot be anticipated that you can have 25 years of operation without major service, major maintenance, and maybe even replacements of this part. So it has to be thought in from the start of the project. And we need some kind of climate control system for protection of the electronics in the harsh environment. A clear design specification, system requirement specification, and a clear design strategy is very important. You can call that system engineering also. And the system requirement, they must be compiled down to subsystem level. You can only do that when you have the design strategy, and condition monitoring is useful for risk assessment. So that was very short for electronics and climate. Thank you. I think you are on mute. You're muted, Erik.
Yes, that's right. I had to cough just a few minutes ago. But thank you, Kim. There was a lot of content also from, as you say, that it's limited what you can do in a webinar like this, and it's also limited, of course, what you can do in a relatively small project. But there's a lot of things to consider. So that's just very interesting. So now, before we go to questions, we have time for some comments from the project partners. So perhaps we could start with Rasmus Holmgaard Rasmussen from CS Electric, if you are with us.
I certainly am.
If you could give us your perspective on the project and how you are working with these kind of things.
Well, of course I can. The project itself gave us a lot of new knowledge or new lights into existing projects as we are developing. It's more X2P projects currently. And some of it gave us lights onto the areas that we didn't in CS Electric have the knowledge about. For instance, how to ensure that the painting is covering everywhere on our what's it called? I think called it shell here. Also how to avoid moist inside, and what can we actually obtain by passive filtering of moist and salt and everything. So we actually gained a lot of knowledge into how to avoid a lot of the critical parts that would eventually kill off a system like this. So yeah.
Thank you, Rasmus. And if we have Torbjørn Schrøder from Copenhagen Pump with us, will you also say a few words? Can you see if is Rasmus here? Sorry, is Torbjørn here?
I'm here. Can you hear me?
Okay, now we can hear you. Yes.
Okay. Thank you very much for an interesting project. I think Tool said most of it, but it has been very interesting to work with. Let's say heat transfer and pumps in these sizes, because the kilowatt hours are basically very large, even for the standalone system. And we reach, at least if we talk about the very big system, the centralized system, fastly let's say the upper limit of what pump companies can actually handle in their program. So you are on the top shelf when you are going to suggest pumps for that. For the more, let's say, standalone system, one windmill and one system, it's much easier to find simple equipment. But what I really focused on was what Troels also commented, was the open loop versus the closed loop system, which I really think is something we as let's say a community in general, when we are working offshore, should consider much more, because there is tremendously savings on footprints, and it's basically on all footprints. It's in physical footprints, it's simpler pump constructions, it's less chemical footprint. It's definitely a much lesser or smaller energy footprint you have when you look at these systems. When that's said, it doesn't mean that necessarily that what we call conventional systems with open loop system is cannot be improved, but I really think it's time to challenge the closed loop system, especially for this area, because it's so huge amount of cooling water and energy we are going to operate. And there is really, again, there's a big efforts in lifetimes savings on especially on the pumps when we use the closed loop system. So a lot of investment cost savings and maintenance cost savings. I think that's what it was for me.
Thank you, Torbjørn, and thank you again, Rasmus. Also, it was good to hear from some of the other partners in the project, so you don't all think it's all a project by Force Technology. We also had 5 other industry partners, and they all contributed with valuable knowledge about their particular field and with defining the problems. So it's been a really good collaborative project. So the work will continue here at Force Technology. We are continuing to develop the expertise we have together with various partners. We also develop tests and equipments, and we also offer courses both on safety and on corrosion, for example. As Nanas told you, there's some a demo project coming up and perhaps more in the future. And if you are interested in collaborating in some project, you are more than welcome to contact us. It doesn't have to be about the pumps. It could be about the other subjects as well. We are interested to hear your ideas and thoughts. And you're also welcome to contact us if you just have questions, and we can see if that's something we can help you with. And I think now, before the time runs out, is is a good place for questions. So will someone check in the chat whether anybody has asked questions?
Yeah, I can see there's a question. Etienne has something about what when the IP enclosure protection not is sufficient, what can we then do? And there are other things. They are not just as simple as the IP system, but we use something we call a cyclic humidity test, where we try to accelerate the humidity ingress. And we do that both in this ELMAC project and in the FORCE project with long-lived products. So if you want to know more about that, you are welcome to contact me or one of my colleagues to know more about this. And then there was also a comment on put the electronics in an oil bath. I put a thumbs up for that, because that's also a possibility. But then, of course, you have to ensure that the electronics is fit for that purpose, and you have to be sure on how to get the electrical connections in and out of that oil bath. But it's certainly a possibility, and it's one remedy you can use. Thanks.
That's very interesting. Any other questions here before we move towards the end? Doesn't seem to be the case. And you're of course welcome to contact us afterwards if you have any pressing questions that you didn't have time to write now or didn't think about now. So before I leave you, I just want to give you a quick ad here for our Power-to-X safety courses about the risk and safety in operation and maintenance when you're producing hydrogen. And if you're interested, you can look it up on this homepage here, and it's something that is offered in both Danish and English. And with that, I just think I want to thank you all for your attention and for participating today. Feel free to contact us. We will share the slides sometime within the next few days. You are welcome to also share them with your colleagues. And if you contact me, I'll be happy to pass on your questions to the most relevant of my colleagues here.
Yeah. I just saw, Erik, there was a comment about this condition monitoring system. It's about this actual sensor, the mission profiling sensor. It's developed by the main project lead is on DTU Mechanics. So they will probably make some kind of sub company that will make this one, or take it out to some of the project partners. And the other one with the moisture level indicator, it's something that it's basically a part of the printed circuit board design. So it's not that it's a sensor somebody own, but at FORCE we can do consultancy on how to make it and how to calibrate it and work with it. Thanks.
Interesting. And of course, there is a bit more time before we have to end. So are there any more questions now that we are through all of the many slides? Otherwise, I'll leave you to go and continue the rest of your day, and I'll do the same. And feel free to contact us and stay in touch if you want to hear more about future projects. Thank you.
Thank you.